let's take a look at our final topic in Calculus 1, Section 4.9, Antiderivatives. Now, we're just going to touch on antidifferentiation in this course, but in Calculus 2, Math 202, that's what you spend almost the whole time doing, is antidifferentiation. So we're going to look at the very basics of this. After limits in this class, we spent all of our time taking the derivative, learning various derivative techniques, applying these techniques, etc. I give you a function, you give me the derivative. I give you f, you give me f prime. What if it worked backwards? What if I gave you f prime and you had to figure out what f was? In other words, what if I gave you a function and you had to tell me what function it was the derivative of? If we consider two functions, big F and little f, if big F prime equals little f, then big F is the antiderivative of f, of little f, that is. So I could say find the antiderivative of each of these functions, right? So if you've already seen this before, you might notice that I'm going to be missing something in each of these problems. Just hang with me for a sec. Number one. By the way, I'm always going to refer to the antiderivative as the capital letter, right? So I'm going to say big F of x equals, well, if you think about it, all we have to do is the power rule in reverse, right? What function gives us 4x cubed derivative, right? Well, if you think about it, it's going to be x to the fourth. Notice that I just did the power rule in reverse, right? And you can just check, right? Take the derivative of x to the fourth, get 4x cubed. Similarly, x cubed is the antiderivative of 3x squared. Now, be a little careful with x. It might be tempting to say x squared, but if you take the derivative of that, you get 2x, not x, right? So you might think it's x squared, but you say, wait, no, we have to put a 1/2 in front of it to cancel out that 2. Okay? Now, again, I'm missing something here, but we're okay for right now. For s of t, well, again, capital S of t, it's going to be something like 2t to the 7th, but when I take the derivative of that, I get 2 times 7t to the 6th, right? See how we didn't want the times 7 there, so we have to divide out by it? So I guess that meant that we had to divide out by it there, right? So that's just sort of the scratch work. I'll erase that, but that's the exact sort of reasoning you want to use, okay? Now, what about x to the n in general? Well, I guess you could say, if you think about it, what's the pattern that we've been doing, with each of these and with this? I guess it's that, well, look, we're raising x to the n plus 1. We have to add 1, right? We're doing the reverse of the power rule, right? But then if you took the derivative of that, you'd get n plus 1 x to the n, right? And we didn't want that. We just wanted x to the n. So we divide out by the n plus 1. Right? So I guess that means that over here, we do 1 over n plus 1, x to the n plus 1. Okay? And so this, I'll just erase that work, is what I call the reverse power rule. No one uses this term. I'm not sure why, but I like to call it the reverse power rule, because you're doing the power rule in reverse. Instead of bringing down the power and then subtracting 1, you're adding 1 and then dividing. Okay, it's the opposite. Now, what about the antiderivative of 1 over x? Think about that one for a sec. The answer is y equals ln of x. Now, some people are sticklers and they want you to say ln of the absolute value of x. I don't care. Do whichever one you want. But wait a minute. Y also equals x to the negative 1, doesn't it? Well, I guess then maybe we ought to be a little careful and go back here and say, well, hold on a second. I guess the antiderivative of x to the n is this guy for n not equal to negative 1, right? And if you think about it, we'd be dividing by 0 when n equaled negative 1. But I guess we have ln of the absolute value of x when n does equal negative 1. All right. Now, anyway, let's take a look over here. All right. I guess, well, I'm not exactly sure what this should be. But I do know that little f of x equals negative 2x to the negative 5/3. That might be easier, right? Because now I don't even know what this is going to be, but I do know that using this reverse power rule, I can just say, okay, it's going to be negative 2x to the negative 5/3 plus 1, and then all of that divided by negative 5/3 plus 1. See how I didn't really even think right there? Right? I just applied the formula. Now I can do the simplification, right? Negative 2 x to the, I guess 1 is 3/3, so I guess this is negative 2/3. And then it's all divided by negative 2/3. Whether you divide all of it by negative 2/3 or just the coefficient, it doesn't make a difference. And I guess if you simplify that, you get 3x to the negative 2/3, right? Did I do that correctly? I think I did. Right? And the nice way to check your answer is just to say, okay, let's take the derivative, right? We take the derivative, we get 3 times negative 2/3 x to the negative 5/3. And look, the 3's cancel, we have our original expression, right? So that's one nice thing about antidifferentiation is you can check your work. You can check your answer if your differentiation is good. Now, if you've seen antidifferentiation before, you might be saying, oh, plus c, Dr. Halpern, plus c. Well, here we go. What if we added any constant to our antiderivative, right? Let's go back to number 1. Right, we found the antiderivative of this guy. What if I added 1 to this, and we took the derivative? Wouldn't that also give us little f of x? Well, it would, right? Because plus 1, that's just a constant. What if I said plus 10, or plus a billion or something like that? I don't know, right? So I guess if we added any constant to our antiderivative, that would also be an antiderivative. So I guess I'll just write here adding a constant to an antiderivative gives another antiderivative. I'll state this a little more formally on the next page. So, always add c. Okay? So if we go back here, we write plus c. Plus c. Plus c, plus c, plus c, plus c, plus c, plus c. Alright? So, fact 2. If big F is an antiderivative of little f, then so is f of x plus c for any constant c. The convention's that you put a capital letter. Okay? Now, one thing about antidifferentiation, again, we're looking at the very basics of this. This can get hard very quickly. Certain things that are pretty easy to look at, and might even be easy to differentiate, right, take the derivative of, can actually be very challenging to antidifferentiate. They might even be impossible, right? Now, again, we're sticking to the basics. Let's take a look at a couple more examples. Example 3, right? Find the antiderivative of each of these, right? Well, first of all, f of t equals t to the 1/2 plus 4 sine of t, right? So just like differentiation, I think it's easier to change the radicals into and fractions into exponents or powers. You can do whatever you want. So big F of t is going to equal, well, again, I don't exactly know what it's going to be, right? We're going to be adding 1, dividing, what's going on? It's just going to be, leave a space in the front, t to the 1/2 plus 1. Actually, I'll do it this way. Yeah, no, that's fine, actually. T to the 1/2 plus 1 all over 1/2 plus 1. All right, now think. What is the antiderivative of 4 sine of t? It's not plus 4 cosine of t. It's minus 4 cosine of t. Right? And then if you think about it, we wind up getting, right, 1/2 plus 1 is 3/2. So dividing by 3/2 is the same as multiplying by 2/3. So 2/3 t to the 3/2 minus 4, what? Cosine of t, right? Plus c. Very good. Remember your plus c. Okay. Really, we should have written one here too, but I wouldn't take off if you forgot it. Right, just put it at the end, right? All right, so let's see what we've got here. F of x equals secant of x plus secant of x times tangent of x. Big F of x equals secant of x, yes, plus c, right? Just like with ln of x, right, or with the 1 over x, rather, sometimes you just have to know it. Sometimes you just have to look at an expression and say, oh, that's the derivative of this function, right? No reverse power rule, no simplification, just straight up, oh, I remember that one. Okay, so that's that one. H of x equals cosine of x squared. Pretty straightforward chain rule problem, pretty reasonable expression to look at. It turns out big H of x does not exist in what we call a closed or elementary form. Meaning that you can't write this as a finite collection of terms with plus, minus, times, divides by square root, etc. You can't do it. You can use something called a Maclaurin series or whatever to get an infinite limit with an infinite number of terms, but that's not what we call elementary form or closed form, right? And to figure out to know why you can't antidifferentiate this, it's actually very tricky. It involves extension fields and stuff you learn in advanced abstract algebra too. So just trust me when I say it doesn't exist. You can plug it into Mathematica. It'll tell you it doesn't exist. And I would never give you a problem like this. But I just want to point out that this is an example of how antidifferentiation can go awry. Something pretty basic, turns out, doesn't exist. All right, last but not least, antidifferentiate this. Well, if e to the x is its own derivative, then it's its own antiderivative. And then what about that last term? You recognize it? It's arctan of x plus c. Right? All right. Now, sometimes we just are given a general function. We write plus c and we're done with it. Sometimes we're given a word problem, or something else. Whether it's a word problem or just a problem, but there's something called an initial condition, which means there's an extra piece of information, and we're able to solve for c. Let's take a look at an example. Suppose we have a particle whose velocity is given by this function. Somehow we know the velocity function, but we want to find the position function. We also know that at time 0, I guess at the start, the particle starts at position -2. So the question is to find the position function s of t, right? Well, let's think about it. Normally, we have the position, and we take the derivative to get the velocity. So if we're given the velocity and we want the position, then we take the antiderivative. So I'll say antidifferentiate v of t. So we get s of t, which is the position function, is going to equal, what's the antiderivative of t squared? Yep, it's 1/3 t cubed. Now be careful, this is plus cosine of t, all right? Plus c. Okay, so normally if I just gave you this as a general problem, no initial condition, then that would be your answer. But I tell you, s of 0 equals -2. So we have a little bit more information that we need to work with. So s of 0, on the one hand, that equals -2. On the other hand, by definition, that equals 1/3 times 0 cubed, or I'm just plugging 0 in to our function. So maybe right here, initial condition. Maybe I'll highlight it too. Okay. So we get this. That implies that, okay, so this goes to 0. Right, we should know that. Cosine of 0, we should all know, is 1. 1 plus c equals negative 2, and that implies c equals negative 3. Maybe I'll write that right here. So, and you have to write this as your final answer, s of t is really 1/3 t cubed plus cosine of t minus 3, right? You see how we have a specific answer for c? That was thanks to our initial condition. So then the question is, why is this true? Why does it work this way? Well, if you think about it, remember from curve sketching and, Max-Mann's concavity stuff, the derivative and second derivative and antiderivative, all of the derivative stuff tells us about the shape of the curve, about the behavior of the curve. What it does not do is it does not tell us about the location of the curve, right? So, for example, if we have this curve, right, s of t equals t squared minus sine of t, that tells us what the curve looks like, right? It's a parabola-ish kind of thing, right? Relatively parabolic, not perfectly. The sine kind of messes it up a little bit. But what it doesn't do is it doesn't tell us where the curve is. But if we add c to it, now I let c be a range of values from -5 to 5, it could be any one of these curves. Note that each of these curves has the exact same shape. It's just they're shifted up or down depending on what c equals, right? And then if we take a look and we say, oh, s of 0 equals -2, well, then I guess we know that that is our function in question, right? And note in that case that, right, oh, shoot, I'm sorry. This shouldn't have been t squared minus sine t plus c, right? This should have been, sorry about that. I guess this should have been 1/3 t cubed plus 4 cosine. Sorry about that. Cosine of t plus c. There you go. All right, so there we go, right? We have that guy. Right, was that our... Oh, no, sorry, not plus 4 cosine t. Plus just cosine t. My bad. There, that makes much more sense. Okay. Right, there's our point, right? Right, and so at that point we say, oh, okay, look, 0, -2. This is what it would have been if c had been equal to 0. So that's our answer, okay? Let's just crop this a little bit. I guess I'll just do that. There we go. Okay, something like that. Right, so anyway, once we have a single point to anchor the curve, like this guy, we know the way the rest of the curve must behave. Okay, so that's the importance of the initial condition. It tells us where the curve is. All right. Another example here, I refer to the function I give you as f prime, and you need to find f, right? So anyway, let's just do this out. All right, we get that. We get that. Here we have the same thing. Except now we have f of 0 equals 9. Well, that equals 8 times 0 plus c equals 9 implies c equals 9. So f of x equals 8x plus 9. And remember, with an initial condition problem, I need you to write the final specific particular function, right, for full credit. Last but not least, gross, right? Part D. Here, f of x equals, well, let's just do it out, right? It's going to be 1/3 times 1/8 x to the 8th minus, 2/3, times, I guess if you add 1, that's 5/3, so it's going to be 3/5 x to the 5/3, right? Because dividing by 5/3 is multiplying by 3/5. And then we add c. Okay? F of 0 equals 0 minus 0 plus c, which equals 1. So f of x is going to equal 1/24, right? Just simplify that a little bit. Minus 2/5 x to the 5/3 plus 1. All right, that's our answer. All right, now let's look at a couple more problems, right? A couple word problems, right? Here we're given a car's acceleration, right? A car's acceleration. We're also given the car's initial position and the initial velocity, and we want to find the position function of the car. So remember, we take normally we're given position, we take the first derivative, we get velocity, we take the second derivative, we get acceleration. So with acceleration, we have to go back once to get velocity, back again to get initial position. So we have v of t equals 1/3 t cubed minus 2t squared plus 6t plus c, right? Remember the plus c. Now remember, we're given that v of 0 equals 5, which is 0 minus 0 plus 0 plus c equals 5. I just want to point out, I know I do a lot of s of 0, v of 0, etc. It might be something like s of 1 equals, or v of 1 equals, and you have to plug in 1, okay? Just to let you know. Right, so anyway, here it works out pretty nicely that c equals 5. Right, so v of t really equals 1/3 t cubed minus 2t squared plus 6t plus 5. Next up, s of t equals 1/3 t cubed. Oh, sorry, no, sorry. We're taking the antiderivative of this again, right? So we get 1/12 t to the 4th minus 2/3 t cubed plus 3t squared plus 5t plus, I'll call this guy d. Right? And then we have that s of 0 equals 3. Well, that's also equal to 0 minus 0 plus 0 plus 0 plus d equals 3. So so d equals 3, and s of t equals this guy. All right, so that's our answer. Right, so note that we just anti-differentiated twice, and we had 2 initial conditions, which we needed to get a specific answer. All right, similarly, same sort of thing here, right? Let me change this up a little bit. Instead of s of 0 equals 3, let's do s of 1 equals 3, okay? All right, so anyway, we take the antiderivative. V of t is going to equal t squared plus t plus c. V of 0 equals c, right? 0 plus 0 plus c. Maybe I'll just be clear about that. 0 plus 0 plus c, which equals -2, implies c equals -2. So v of t equals t squared plus t minus 2. Next up, s of t equals 1/3 t cubed plus 1/2 t squared minus 2t plus, and I'll call this d. Now let's remember that s of 1 equals 3. Well, that's going to mean that s of 1 equals 1/3 times 1 cubed plus 1/2 times 1 squared minus 2 times 1 plus d equals 3. So what does that mean? That means that 1/3 plus 1/2 minus 2 plus d equals 3. Right, you see how it's really just an algebra problem at this point, right? So that's what, 5/6 minus 2. So that implies -7/6. I think I'm doing that correctly. Plus d equals 3. And that implies that d equals 4 1/6, or that should be 25/6. So, final answer, s of t should equal 1/3 t cubed plus 1/2 t squared minus 2t plus 25/6. Let's do a couple more antidifferentiation problems. Antidifferentiate the following. Now remember, before I even do this, I just want to point out that there are 3 possible methods to antidifferentiate a function. Number 1 is the reverse power rule, right? That's just the 1/n plus 1 x to the n plus 1, right? Number 2 is memorize. And this I just mean, like, for example, 1/x goes to ln of the absolute value of x. Right? You just have to remember that one. And then number 3 is simplify first. Right? Simplify, then go back and do numbers 1 or 2. So let's look at number 1, right? I think before we do anything, we should write this as f of x equals secant squared of x minus 6x to the -1/5 plus 7x squared. Right? So then we know that big F of x is going to equal, what's the antiderivative of secant squared? It's just tangent, right? You just have to remember that. Okay? Now this next one's a bit annoying, right? This is a reverse power rule, right? It's going to be 6x to the 4/5, right? Because we added 1. And then just whatever you get up there, just divide. Right? And if you want, you can clean this up a little bit, right? You can simplify it. I won't require it, really. And that's going to be 15/2 x to the 4/5. Okay, so that's our answer. Yeah, right. G of x equals, and then we've got x to the 2.5 plus 5x to the 1.5 minus 2x to the -0.5. You can also write them as fractions if you want. So big G of x equals, I guess that's 1/3.5 x to the 3.5 plus, I guess that's 2x to the 2.5, right? Because 5/2.5, right? That's just 2. Minus, I think it's going to be 4x to the 0.5 plus c. Yeah. So I get that. And then again, h of x. Oh, right. This one is actually a little too complicated. Let's do this. Yeah, this is a Calc 2 problem unless I make that 3 a 2. Okay, so it's sine of x over cosine squared of x, right? All right, now, if we zoom out a little bit, though, I think this is more reasonable, right? We can write this as h of x equals, well, hold on a second, ln of e to the x, what's that equal to? It's x, right? Ln of e cancels out. We should remember that. And then this requires a little bit of cleverness, but we can write this as 1 over cosine of x times sine of x over cosine of x. So big H of x is going to equal 1/2 x squared minus, oh, sorry, actually, let me write this. This is x minus secant of x tangent of x. So big H of x is 1/2 x squared minus secant of x plus c. Maybe I'll put that down there. Whoop. All right, couple more examples, right? Example 2, right? Find f of f double prime of x equals that, right? Now, note that I don't give you any initial conditions, so we're going to have a couple of extra constants here, right? There's no quick way to do this. You just have to anti-differentiate twice, right? And this will be 7 over 5/2 x to the 5/2. I guess it'd probably be a good idea to simplify first. Let's do that. I guess we're getting 14/5. All right. And so then that implies that f of x equals 1 over 42 x to the 7th minus, I can't do that in my head, 14/5 times 2/7 x to the 7/2 plus cx plus d, right? C is a constant, but right, the antiderivative of any constant is just that constant times x. And now we have to add another constant, right? And I guess we can simplify this a little bit. This is going to be minus 4/5, it looks like. All right. Now, let's take a look at a slightly more in-depth problem, right? This is far beyond something I would ever ask on a quiz or an exam. But I do hope you understand where we're coming from here, because this is a beautiful application of just one piece of knowledge and anti-differentiation. And look how much information we can derive from this, right? This is straight up physics right here, right? A ball is thrown upward with an initial speed of 48 feet per second from a cliff that's a certain height off the ground. Find the position of the ball, amount of time it takes the ball to hit the ground, and the velocity they hit the ground, okay? So the only thing you need to know, and if I ever gave you a problem like this that I would tell you, is since we're measuring in terms of feet, the force of gravity causes an acceleration to be, I guess I should say, let a of t equal negative 32 feet per second squared. That is the acceleration of gravity in terms of feet. It's not perfect, but it's pretty close. It's a good approximation. It's a nice whole number. We're going to use it, okay? So, okay, I guess we know that. So we throw the ball up with an initial speed of 48. Okay, so I guess if we know the acceleration, we know that the velocity of the ball, to be clear, we're finding the position function of the ball, right? So we're going to find the velocity, then we're going to find the position, right? Anti-differentiate twice, right? The velocity is going to be negative 32t plus c. I guess we know that since v of 0 equals 48, you see where I'm getting that from? we have v of 0 equals negative 32 times 0 plus c equal 48. And that implies c equals 48. So v of t equals negative 32t plus 48. Okay, so we've got that. Since we're trying to find, again, the position function of the ball, we can just anti-differentiate v of t, right? So s of t equals negative 16t squared plus 48t plus, I'll call this d. Actually, maybe I won't skip a line for now. I'll put it up here, right? And I guess we know that S of 0, right, the initial position of the ball is 432. Right, we have, so let me just put this all up here. It's kind of a visual eyesore, right? We have S of 0. Well, on the one hand, it equals 432. On the other hand, it equals 0 plus 0 plus d equals 432. And that implies that d equals 432. So S of t equals negative 16t squared plus 48t plus 432. All right, so we've got our position function of the ball. So if we maybe I'll underline it like this. I'll put a check. Maybe I'll underline this. Amount of time it takes for the ball to hit the ground, and then maybe I'll do this. So next up, we're going to try to find green. Amount of time it takes for the ball to hit the ground. So if you think about it, the ball started at position 432. We want to know how long it takes for the ball to hit position 0. Well, if we have a position function for the ball, then let's just set the position function equal to 0 and solve for t. So I'll say now, let S of t, which equals, you know, all this nonsense, equals 0. So if we solve for t, right, so what we can do is divide by negative 16, and we're going to get t squared minus 3t, and 432 divided by negative 16 is going to be negative, I want to say it's 22, right? So it's 112. How many times does 16 go into 112? It might be 7, right? Because you take away 16, 144. Take away again, you get 130, 120, 144, 128, 120. Yeah, I'm pretty sure it's 27. Right? Right? So we get that. Doesn't look like you can factor that, right? So we're getting that t equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And that winds up equaling 3 halves plus or minus root 117, awesome, over 2. That may not be the worst thing, though. Let's see, can we simplify that at all? Not that we have to. You can pull out a 9, right? You can pull out a factor of 9. That's 9 times 23, right? 9 times 23. So I guess if we wanted, we could write this as 3 over 2 plus or minus 3 root 23 3 over 2. I guess if you wanted, right? Just making sure about that. Oh, no. 13. I'm sorry. 13. Right, 9 times 13 gives us that. Yeah, okay. All right, so anyway, we get that. Now, do you see that that is our answer to the green problem? The amount of time it takes for the ball to hit the ground is that many seconds. I guess we should put seconds. Okay. Last but not least, it says find the velocity at which the ball hit the ground. Now, this is a little tricky. But what you need to notice is that, well, we know what time the ball hits the ground. We just need to know how fast it's going. Well, we know how fast it's going at any given time thanks to v of t. So we're just going to find v of this gross stuff. And I'm not actually going to do this out. I'll leave that to you. Right? That's kind of nasty. And whatever it is, it's going to be feet per second. So that's how you do it.